Welcome back to the Deep Dive. Today we are taking a look at a fascinating shortcut. We're digging into the world of materials testing and tackling one of the biggest bottlenecks in advanced manufacturing, this constant battle between speed and safety.
Exactly. We're talking about components that they absolutely cannot fail. Think about parts inside a jet engine, maybe medical implants, or even high-speed rotors.
And these are all things that are increasingly being made with additive manufacturing, 3D printing basically. It gives you this incredible design freedom.
It does. But when you build something layer by layer, especially with these high-performance metals like nickel superalloys, you introduce a lot of complexity and, potentially tiny defects.
Right. So the crucial question stops being, can we print it? And it shifts to, will this thing actually last? Will it survive millions and millions of cycles of stress?
And that's the whole idea behind high cycle fatigue, or HCF. Even like microscopic flaws can just drastically cut down the fatigue life of a part compared to a traditionally forged one.
So if you're certifying a part that's safety critical, you need to know with absolute certainty that it can handle that stress pretty much indefinitely.
And here's the problem, the core dilemma. Traditional testing is just painfully slow.
To find the fatigue limit, that's the magic number, right? The stress level it can handle forever.
That's the one. And to find it, you have to run what's called an SN curve method.
Yeah.
You're testing multiple samples up to 10 million cycles.
10 million? That's a huge number.
It is. That can take months, sometimes half a year. It burns through equipment, material, time. If you're trying to innovate quickly, that wait is just an innovation killer.
It's a massive roadblock. So let's unpack this. Our sources today are detailing what could be a revolution in this space. It's an accelerated technique called infrared thermography, or IRT. It's sometimes known as the Risotano method.
And it uses heat. It essentially maps heat on a material to find that critical failure limit almost instantly. It lets you bypass all those millions of cycles.
So that's our mission today, to figure out how exactly heating up a piece of metal can tell you its lifetime, and why this is finally reliable enough for things like aerospace.
Okay, so before we get into the test itself, we should probably talk about the material they were actually studying.
Right, the subject. This was all focused on Inconel 625.
Yeah, and Inconel 625 is a real workhorse in high-temperature environments. It's a nickel-based superalloy. It resists heat and corrosion incredibly well.
Which is why you find it inside things like jet engines.
Exactly. And the way they made it is also really important here. They used wire arc additive manufacturing, or WAM.
Okay, so tell us why that specific process matters so much.
Well, WAM is fascinating because it's fast and pretty cost-effective for making really large metal parts. It basically uses a robotic welding process.
Like a welding arm building something up from nothing?
That's a good way to think of it.
Yeah.
A wire feeds into an electric arc, and it just lays down these layers of molten metal, building up these big blocks or billets really quickly.
So it's very efficient, but I'm guessing that layering process can cause some issues. It's not the same as a single solid block of forged metal.
Not at all. The thermal history, all that constant heating and cooling of the different layers can introduce, microstructural flaws or tiny pores that can really compromise the strength.
Which means post-processing is everything. You can't just print it and put it in a plane.
Oh, absolutely not. And the researchers here did something really crucial. After printing, they put the material through a special refinement process. They physically deformed it or forged it with a high-frequency pneumatic hammer.
So they were basically hammering the 3D printed layers.
Essentially, yes, while it was still warm, around 200 to 300 degrees Celsius. This interpass forging helps crush any of those internal voids or imperfections from the printing process. It really improves the final mechanical properties.
And then a final heat treatment after that, I imagine.
Correct. So you end up with this really complex, highly engineered material, forged and heat-treated layer by layer.
Which brings us back to the big challenge. How on earth do you test something that complex quickly enough for it to matter in the real world? Okay, here's where it gets really interesting. Let's talk about the physics behind this IRT method, because it's using microscopic energy changes to tell you when a material is about to, give up the ghost.
The core idea is something called the self-heating effect, and you can think of it with a simple analogy. Imagine you take a paperclip, and you just bend it back and forth, right at the same spot, really fast.
It gets hot.
It gets hot, exactly. And that heat isn't coming from nowhere. It's the result of internal friction, of energy being dissipated as the material's structure is damaged on a micro level.
So if you bend it just a little, within its limits, it stays cool.
Right, it's absorbing that energy elastically.
Yeah.
But the moment you start bending it too far, you're causing permanent damage, and that damage literally shows up as heat.
And that's the exact same principle they're applying here for high cycle fatigue.
It is. When a material is cyclically stressed below its true fatigue limit, the energy it dissipates internally is tiny, almost negligible. But the second that stress amplitude goes over that critical limit, the damaging process kicks in. We're talking microcracks starting to form, dislocations moving, and all that activity releases a measurable amount of energy.
And that energy release is converted directly into a rise in temperature on the surface.
Yes, so by watching that surface with a super sensitive infrared camera, the researchers can pinpoint the exact stress level where the temperature curve suddenly breaks or kinks and starts shooting upwards. That kink point, that is the fatigue limit.
That is just such an elegant solution to a really massive problem. What kind of setup did they use to actually capture such a subtle heat signature?
They needed to cycle the material really, really fast to generate enough heat in a short time. So they used a high-frequency resonant testing machine. It was basically pulling and relaxing the material samples at 125 hertz.
125 times a second.
Every second.
Yeah.
It simulates the kind of constant vibration you'd find in, a high-speed engine.
And to measure that temperature shift, which could be tiny, they must have needed some seriously sensitive gear.
Oh, absolutely. The infrared camera they used had incredible thermal sensitivity. It could detect temperature changes as small as 0.02 of a degree Celsius.
Wow.
And that precision is key because you want to see the damage starting long before the material actually feels warm to the touch.
I love this detail from the source material, though. For all this high-tech equipment, they still had to coat the specimens in simple black matte paint.
It sounds low-tech, but it's so important. Different surfaces reflect infrared light differently. By coating everything in a standard black paint, they ensure a uniform emissivity. Basically, every sample radiates heat in the exact same way, which eliminates measurement errors you'd get from a shiny or uneven surface. It guarantees consistency.
Okay, so we know the science, but the key word here is accelerated. If they ran the test for hours, it kind of defeats the purpose. How did they speed it all up?
That all comes down to the testing strategy. They use something called block cyclic loading. This isn't one long, continuous test until the part breaks.
Right, you said it's more like a series of short sprints.
Exactly. They didn't just crank up the stress until failure. They ran 11 successive loading blocks. They'd start at a baseline stress, say 300 megapascals. And then in each new block, they'd just nudge the maximum stress up by a small, steady step, about 10 to 20 MPa at a time.
And the really clever part is that after each short block, they let the sample cool all the way back down.
Yes, you reset the thermal baseline. That ensures that when you start the next block at a slightly higher stress, you're only measuring the heating effect of that new stress level. You're not getting any cumulative heat buildup.
So within each of those short blocks, how did they know when to stop and collect the data? The sources mentioned 3 stages of heating.
Right. So typically when you start stressing a material, the temperature goes through 3 phases. Stage 1 is that first quick temperature increase. Stage 2 is where it stabilizes heat and equals heat out. And stage 3 is that runaway heating right before it fails.
And waiting for stage 2 for that stabilization would still take too long.
Way too long. And that's the secret to the acceleration. They decided to use the rate of temperature increase, that's called theta dot, right at the start of the block. They focused only on stage 1. They never even waited for stabilization.
That's the shortcut. So instead of waiting for the temperature to flatline, they just measured that immediate spike. It's like flooring it in a car and only measuring how fast the speedometer needle jumps in the first second, not waiting to hit your top speed.
That's a perfect analogy. It's pure efficiency. By using the rate of temperature rise, they only needed between 6,000 and 12,000 cycles for each block. That's what cuts the test time down from months to, hours. You get the critical piece of information when the damage mechanism turns on without the huge time sink.
Okay, so they have all this heating rate data. How do you turn that short-term thermal response into a precise long-term fatigue limit?
This is where the data analysis is just...
Yeah.
It's fascinating. They apply a really sharp, simple mathematical logic to it. They take that rate of temperature increase from each block and they plot it against the maximum stress that was applied in that block.
And what does that graph end up looking like?
It creates this really clear picture, a graph with 2 very different slopes. Below the true fatigue limit, the plot is almost flat, a really shallow slope. The material's fine, it's not dissipating much energy, but the instant you cross that fatigue limit, the slope of the line becomes dramatically steeper. Damage has started, and that internal energy dissipation just skyrockets.
So the fatigue limit is the exact point where those two lines intersect.
Yeah.
Where the slope abruptly changes.
That's the definition. And to make sure it wasn't just subjective, someone just eyeballing the graph, the researchers used a statistical analysis. They mathematically found the cleanest, most consistent split between those two branches by maximizing something called the combined coefficient of determination.
So they made sure the result was based on objective math, not just someone squinting at a chart, which is obviously key for certification.
It is. And the analysis showed the highest consistency actually happened after just the fourth loading block. They really only needed 4 of these short thermal tests to reliably find the answer.
That's incredible. So after all that, running a few different analysis variants, how consistent were the final numbers?
They were remarkably tight. The mean fatigue limit they got from this accelerated IRT method was 383 megapascals. And the internal variation between their different test runs was less than 0.5%, only 0.46%. To get that level of precision from such a short test is, well, it's astounding for material science.
So let's get to the bottom line. What does this all mean? We have this rapid, precise answer, 383 MPa. How did that compare to the old, slow, traditional method?
Right, this is the validation step, the most important part. They didn't just stop there. They also ran the full traditional SN curve tests on identical specimens from the same batch of inconal, pushing them all the way out to 10 million cycles.
And what did the gold standard, the time-consuming test, finally reveal?
The traditional fatigue limit, based on a 50% chance of failure at 10 million cycles, came out to be 399 megapascals.
Okay, so 383 versus 399, a difference of 16 MPa. That's really close.
It is. And the crucial takeaway here for you, the listener, is the percentage difference. The accelerated result was only 4% lower than the traditional one.
Let's just pause on that. 4%. That small number is the difference between waiting months for an answer and maybe getting it in a couple of weeks. That's a complete game changer for industrial timelines.
Absolutely. The sources really emphasize that this 4% difference it's considered insignificant when you account for the natural scatter you always see in traditional fatigue tests. If anything, the IRT method gave them a safe, slightly conservative estimate of the true limit.
So safety is maintained, but time is just drastically cut down. And these results also lined up with other data for Inconel 625 made by other methods, right? Which is another good sanity check.
It is. Those values are usually around 400 to 450 MPI, so this WAM material is performing right where it should be. And all this agreement really justifies using this Risitano IR2 method for rapidly certifying these nickel-WAM alloys. It enables a huge reduction in the number of expensive specimens you need and, more importantly, the total test time.
Think about the economic impact of that. If you're a company developing a new metal powder or a new printing technique, instead of waiting half a year to see if your innovation works, you get a reliable answer in a few days. That speeds up the entire R&D cycle for aerospace, for energy, for automotive. This is how you finally bridge that gap between rapid manufacturing and absolute safety.
This brings up a really important question, though. We've seen this technique is highly effective. It's validated for these complex WAM nickel alloys. This suggests that this infrared heat mapping isn't just a niche tool. It could be a powerful, almost universal assessment method. So how broadly can we apply this approach to instantly check the safety of entirely new materials being developed by 3D printing right now? Could this shrink the R&D cycle for materials that haven't even been invented yet? Something for you to mull or explore on your own.
That capability for rapid assessment, that really is the future of materials engineering. We'll leave you with that thought. Thank you for diving deep with us.